this is last lecture. This is the last part of my lecture, and I think it's also the last lecture of this workshop. And maybe let's thank the organizing session. Okay, so let's continue. Yeah, so we constructed this characteristic class, and now one needs to show that it is non-trivial, because if it is zero, it will other things. So how to show that this characteristic class is indeed non-trivial and unstable? We need to construct interesting bundles. So, what are the bundles we consider? Let's take a formula dimension x, and let's take this k times stabilization. Now, for each, we have a diffeomorphism fi for each I equal 1 and k. So this is a diffeomorphism. This is a diffeomorphism of this k stabilized manifold. It's just defined to be a connected sum of identity map. We just connect the sum this identity map x2 plus x2. This left for one of them to use this reflection. So we remember. So all that we have a reflection diffeomorphism on S2 plus S2, which we discussed yesterday. So we use that reflection diffeomorphism on the K on I subdomain. So for the other parts, we just use the identity part. We just use the identity map. Then this gives us a diffeomorphism fi for each I between 1 and k. And now what do we do? Okay, so one observation is that for different values of i's, this diffeomorphism actually, the support of these diffeomorphisms are destroyed, because fi is supported on i's side. And that implies these fi's all commutes with each other. Having this commuting diffeomorphism allows us to generalize this Luperman's argument. We can take the multiple mapping torus. If you have two diffeomorphisms, in general, you cannot take mapping torus so that the monodromy on the two generators are each of them. But if they commute, then we can do that. Yeah. Okay. So we can take multiple mapping torus. That gives us a bundle. I'll just denote it by P over T. K is just a k-dimensional torus. And now and one needs to prove a proving theorem which states that okay, just now we constructed a characteristic class using Seiberg-Witten theory. Right? So the Witten theorem tells us that if you evaluate this characteristic class on this multi-mapping torus, it just equals the sum of species structures. They are summing species structures whose expected dimension equals negative k. Of course, we need to pick one representative in each conjugate pair. The Seiberg-Witten invariant of x, just a second. No. Expected dimension. The Seiberg-Witten invariant of x with respect to this species. Okay. So basically, it's just the sum of spin Seiberg-Witten invariant among all spin structures. But if we know if x has a unique Seiberg-Witten basic class up to conjugacy, namely if there is only one pair of s such that this number is non-zero, then you just get one. Okay? Of course, we need to find some special x such that it has a unique Seiberg-Witten basic class. Fortunately, this is the case in many of the situations. For example, I think Tom mentioned this Witten's computation of Seiberg-Witten invariant for algebraic surfaces, and one can prove that for algebraic surface of general type, it does satisfy this condition. It has a unique Seiberg-Witten basic class.
Sorry, I'm a bit confused. So the right-hand side does not seem to depend on k in any way.
Right. That's yes, because we have for different value of k, we have different bundles. They all evaluate. And we also have different characteristic class, but the answer doesn't depend on k. Yeah, this is a generalization of the Gruen theorem I mentioned yesterday. So used by Ruberman to prove the exotic diffeomorphism. So it follows the steps we mentioned. Okay. So this is how we prove that the characteristic class is non-trivial because it evaluates non-trivial on certain bundles. And also to show that it's unstable, well, we just observe that if you do a connected sum with S2 plus S2, the Seiberg-Witten invariant becomes 0. Okay. So Seiberg-Witten invariant of X connected sum S2 plus S2. Okay. This is the vanishing theorem for Seiberg-Witten invariant. If you take the two four manifolds with b plus greater than 0, you do connected sum, the Seiberg-Witten invariant is just 0. So this is unstable. So the rest of the problem is to finding enough x so that it covers all x can cover all four manifolds up to stabilization. That's fine. There's some work to do. We have, if you look at the classification of irreducible four manifold, there is this surface of general type. There are this symplectic four manifolds which do not satisfy the Noether inequality, hence they are not tailored. But in all these ranges, one can find enough examples with a unique Seiberg-Witten basic class. So one can find sufficiently many x which detects its two values for any four manifold, but any simple thing. So this is the sketch of construction of this unstable characteristic class, and I want to use one more application of this idea This is due to Torelli and Milnor. So what do they prove? Here is the theorem. There exists simply connected two manifold. There exists simply connected two manifold X, simply connected pairs. For example, X is this K3 connected sum S2 plus S2. That's one example. Yes, okay. There exists simply connected cross performance X such that mapping class group of X is infinitely generated. One can also enhance, Torelli also prove a slightly stronger result, saying that for this X, you can also find example X such that the module of the moduli space is infinitely generated. Okay. But let me just say the mapping class group. So the mapping class group is infinitely generated for some four manifold, for some even simply connected four manifolds. Why is this significant? Because this is another thing that do not happen in other dimensions. So, for example, we know the mapping class group of a surface is generated by 3 or 4 dentwists, depending on the genus. And the mapping class group of any 3 manifold is also finitely generated. In higher dimensions, a result of Dennis Sullivan states that for simply connected high-dimensional manifold, dimension greater or equal to 5, the mapping class group is common measurable with the arithmetic group, hence it is finitely presented. Okay. But this is not the case in dimension 4. So that's that. So this is the significance of this result, and maybe let me just say 1 or 2 words about proof. The proof is really okay. How to prove such thing? How to prove this is infinitely generated? This is just pi 1 of Bmx. So just take its idealization h1 of Bmx in the first logic. Now you want to say that this guy is infinitely generated for some x. How to show a abelian group is infinitely generated? You want to build some surjection to Z infinity. Okay, and also just use the refinement of this. Use a refinement. You just use a refinement. Okay, so the thing I did just now just has one characteristic class in each degree, right? But you can take a refinement and get infinitely many characteristic classes in a fixed degree. How to do that? Okay, so here I'm summing up all spin C structures with a fixed. So basically, here I'm fixing dx. I'm summing all spin C structures with a fixed number of respective dimensions. I need to do this because I need to sum up something so that it's preserved under the monodromy. This is one quantity which is unchanged under any automorphism of H2. Another quantity which is not changed is the divisibility. this is the second quantity, which is always preserved under the monodromy. So you can use this as a second quantity to construct not a single characteristic class in each degree, but infinitely many characteristic classes in a fixed degree. And you just use that as a refinement and detect that this suggests to the infinity. And that implies this such mapping class group has no. Yeah, that implies this pi 0 is infinity projective. Right. Okay. So let's this part. Yeah. Any questions?
Yeah. Is it true also for homomorphism groups or?
Homomorphism group, no, because it's pi 0 of homeo. X, if you assume X is simply connected, this is just the automorphism group of H2. This is due to Friedman, and this is always finite.
Very interesting.
Yeah, so and it's smooth. It's actually a smooth pattern. And I also want to mention that if you drop this simply connected condition, then there are other constructions, for example, bottom to high. The mapping class group of S1 plus E3. Well, let me just say the mapping class group of X is infinitely generated if X is S1 plus E3, S1 plus S3 hyperbolic, so, well, of course, these are not non-simply connected example. And actually, we can also, this is proof not using gauge theory. It's proved using configuration spaces, so-called W3 invariant, which is essentially just starting a space of embedded arcs and use embedded calculus to extract information. And one can generalize this. And states that when mapping class group is infinitely generated, if X is 0, 1 plus a 3 manifold is infinite fundamental group. So you take any 3 manifold, you take the product with 0, 1 interval, and the mapping class group change from being finitely generated to infinitely generated. That's fine.
Question: is there anything like this family Seiberg-Witten business can say about the higher market groups of them?
Yes. So, for example, let's say, for example, Ruberman and Oakley, they have a paper saying that they construct many four manifolds such that IM has this X IM of homeo has large kernel. So yeah, that's also proved using Seiberg-Witten theory. Yeah, also I think one can prove all kinds of many results in this direction. I think another interesting result by David Barradia using family Seiberg-Witten theory states that if you consider the diffeomorphism group of K3 surface, it's not of finite type, meaning that it's it's not homotopy equivalent to a finite, to a CW complex with finite many cells in each field. Because its fundamental group is infinitely dominated.
This last theorem, does it come from Taiwan diff of why is not is infinity generated?
Taiwan is no.
I mean, there exists some results of that.
Yeah. We didn't use that. We used the Bauer diffeomorphism, which doesn't. Okay, Taiwan diff of Y basically use a loop of diffeomorphism on Y, but so still that is level preserving. But here we consider some diffeomorphism which is not level preserving.
Maybe one other question, like, I mean, this result you said above, by building a Y, I mean, this is really about the phi 1. I mean, the S1 cross the N also has the same infinite generation.
S1 cross Dn.
For N big. I mean, this is stuff, like, this is about sort of these different grades.
I mean, they prove results for S1 cross Dn, but not for pi 0.
But there are other works that sort of show infinite generation, and I'm sort of wondering if this lower result you said, is it about 4 manifolds, or is there sort of a hope to get the similar thing for higher manifolds?
I think there is the hope to generalize to higher dimensions also. There should be. The technique behind these results it can be generalized to higher dimensions, unlike gauge theory. Well, gauge theory maybe also can be generalized to higher dimensions. Okay, right? Any other questions? No. Okay, so let's move on to the next part about Seiberg-Witten equations and the singularity theory. So let's start by recalling some basic definition about Milnor fibrations. Milnor F, the Cn map, holomorphic map from Cn to C. For this talk, it's fine to assume F is a polynomial. So let's just and we assume 0 is isolated critical point. Okay. Now, so one interesting thing to study is what happens near this single point. Critical point. The point of which the derivative vanishes. Yeah, okay, it's a singular point of the zero locus, and it's a critical point of the function. Okay. Right, anyway, yeah, well, let's assume 0 is an isolated critical point, and so we hope to understand what happens near this critical point. In general, it's a complicated and very interesting question. So Milnor's perspective is the following. Let's take two numbers, which is beta is much smaller than epsilon and much smaller. Both of them are much smaller than 1. And we can consider. So what can we consider? We can consider E epsilon Cn minus S inverse 0 map to B sums in C means B eta C means a small disk, small ball in C with radius eta. Okay. So if we consider this ball, we move the 0 point, take this image, intersect it with another ball, then this map is a theorem of Milnor. F, let me just call it F2. F theta. It's just a restriction of F. It's a fibration. Okay. And the fiber is just homological. It's defined with so it's called a Milnor fiber. This is a manifold. This is a complex manifold of dimension. Okay. It's a complex manifold of dimension 2n minus 3. Just a second. 2n minus 3. Complex manifold. So I should say complex dimension minus 1. And it's homological equivalent to a bunch of wedges of spheres. And in particular, it only has, this Milnor fiber only have homology in the middle level. It doesn't have any homology in lower and higher. We are going to focus on the case A equals 2. So, okay. And the boundary, this is a manifold with boundary. The boundary of your M is another manifold, is the link of the singularity. Okay, namely it's just F inverse 0 intersect boundary. So this allows us to study the behavior near the singularity by studying this this fibration. Okay. And this is a fibration over a punctured complex plane. You can say it's just a fibration over S1. So you can study the monodromy of this fibration. Okay. And another perspective. Here's another perspective. Alternative. Another thing we can do is the following. We can consider S2n minus 1, which is the boundary of E epsilon. Then this link sits inside S2n minus 1. This 1 is the link. And we have an open book decomposition. S2n minus 1 minus y in the complement of this y, we have a map S1 given by sending, okay, let me just call this rho, sending rho x equals fx over this. So here an open book decomposition of a manifold means a fibration structure in the complement of a codimension 2 submanifold. Just think about a book. Okay, so Y is for the binding of an open book decomposition, and each fiber, the closure of each fiber is called the page of the open book decomposition. So maybe let me write down, let me draw the open book decomposition of S2. So here, I'm drawing a low-dimensional picture, so we remove the south and north pole, and the complement, we get a fibration over S1. So this is the open book of decomposition of S2. And you have many interesting open book decomposition of S3. Basically, any fiber knot will give you an open book decomposition. And for higher spheres, you can create an open book decomposition by thinking about the link near a singularity. Okay, so that's an open book decomposition. And also, I want to mention that studying link is actually something very natural. For example, if we set f to be this polynomial to be what? To be z0 squared plus z1 squared plus z2 squared plus z3 squared plus z4 6k minus 1 with k between 1 and 28. Okay, it's y. Okay, so let's do some dimension counting. Here a equals 5, and y, the dimension of y is 2n minus 3. So y is a 7-dimensional manifold. Right? The link for this singularity is a 7-dimensional manifold. Then you have this number 28 here. What do you think of? This gives 28 smooth structures. Okay, so this is the easiest description of the exotic spheres that I know. I think it's due to Bristol. Yes. So just write down this polynomial, and that gives you exotic spheres. Okay. And now our main focus today will be dimension n equals 2 case. Also I want to mention another example. So for example, another example is f can be z0p plus z1q plus z2r. Well, p, q, r are just 3 integers. Then the link is a 3 manifold. We usually denoted by sigma p, q, r. It's called the Bristol sphere. This is a 3 manifold. This is some important example of 3 manifolds. For example, people study floor theory like these manifolds because they are easier to calculate. Okay. For example, when PQR sigma 235 is the Poincare homogeneous sphere. All right, now. Returning to this open book decomposition. So now, okay, you have this open book decomposition. That gives you, so we can take the monodromy phi of Milnor fibration, monodromy of Milnor fibration, or equivalently, a monodromy of this open book decomposition. I forgot to mention. So if you take a page of this open book decomposition, it's also a Milnor fiber. So Milnor fiber you can define either as a fiber of this vibration or the closure of the fiber of this vibration. It's essentially they are diffeomorphic to each other. So now you can take the monodromy. So whenever you have a vibration over S1, you can take the monodromy. That gives you a diffeomorphism. So give you a diffeomorphism phi, which is well defined up to isotropy. So this is the so we call it the geometric monodromy associated to this singularity. Okay, so it's really the geometric monodromy for singularity is a mapping class of the Milnor fibration of the Milnor fiber. Okay, why do I call the word geometric? Because people actually study more about the induced map on homology. So this is part H2M. Now, whenever you have a diffeomorphism, you can study the induced map on homology. Usually people just call this guy monodromy. So really it's the induced map by geometric monodromy. So maybe we can call it algebraic monodromy, just the induced action on homology. Okay? So this guy plays very, very important role in algebraic geometry, in singularity theory. It has been extensively studied. In particular, there is the following very surprising theorem. Stating that this star, all eigenvalues of this star are unit roots of roots of unity. Yeah, this is proved using highly non-trivial algebraic technique. I don't know analytical proof. On the other hand, so the geometric monodromy itself is less understood, less studied. In principle, it could contain more information because it's by passing to the induced map on homology, you lose some information. So, so the question is, so we hope to understand this geometric monodromy, especially in dimension 4, namely for variable polynomials. And the specific question we are interested in is this finite in the mapping class group? Okay. So is this a finite order element in the mapping class group? Okay. So what's the motivation of this question? The question is basically, okay, we have this Milnor fibration, which is essentially a fibration over S1. Okay. It is certainly non-trivial fibration because the monodromy action is non-trivial on homology. But if we are allowed it to a base change, like pull back this fibration by a degree m map from S1 to S1, or you can say just n4 branch cover from C to C, do we get a smooth fibration? Okay. The answer is, do we get a trivial fibration smoothly? Okay. The answer is yes, if and only if this is a finite order element in the mapping class. Okay. So in other words, does Milnor fibration trivial after a base change? Okay. Yeah. So we want to study this question. This question can be asked in arbitrary dimensions, but we focus on dimension 4. Any questions about the statement of the questions about any of these conditions? No? Okay, good. All right, and now let's do one example for which the answer of this question is yes. It is indeed of finite order, and it is actually, I would say, it's the most important example in singularity theory. It's the simplest singularity which appears in Andreas' talk, when he talked about Lefschetz fibration. There is this singularity model that appears there, and let me recall that example. F both are C3 xyz equals x squared plus y squared plus z squared. Okay. Then the link y is just rt2. The unifier is really just you take the tangent bundle of S2, you take its disk bundle. That's a disk bundle of S2. We reverse the orientation so that the self-intersection number of the zero section becomes -2. And this is the Milnor fiber. Okay, so it's just essentially it's just a unit disk bundle of S2. Okay, and in this case, the monodromy came from M is called the dentist along this S2 S. Okay. S is just a zero section of the tangent bundle. So this is the -2 sphere. -2 sphere is a sphere, an embedded sphere of self-intersection -2. So I believe this appears several times in the class. When you construct a vector vibration structure on K3 surfaces, this sphere naturally appears. Okay. So a schematic picture, a dimensional reductive picture is as well. I guess this is a famous picture. This is a singularity, this is a singular fiber, and the monodromy is what happens when you travel along here. And turns out the monodromy is just a band fixed along this S. And so actually one can make symplectomorphism. Actually, it's a Hamiltonian. It's actually a Hamiltonian isotopy. And phi, in this case, phi we call phi the band-sided twist. Along the Lagrangian sphere. So there is a way to put everything in a symplectic context. In that case, the monodromy will be a symplectomorphism, and it's a Hamiltonian symplectomorphism, and it is actually I mean, it has been studied a long time ago by Arnold, and then Seidel in his thesis proved that this symplectomorphism in a lot of cases where plot is infinite order in a symplectic mapping class group. Yeah. All right. Then okay. So I want to address that question there. So I want to prove that phi. So then phi squared is isotopy to in mapping class group. This is there's very here is a proof of this fact. So I learned this proof from Peter Kortheimer. I think Seidel also learned this from Kortheimer. Yeah. So how to prove this square of this matrix is distributable. Here is the argument. Okay, so first we do a base change. Well, we have this C3 to CF. Then let's just consider a base change which sends W to W square. Okay. Then we pull back this with some algebraic variety x. Okay. So x will be what's x? So x is x, y, z, w, such that x squared plus y squared plus z squared equals w squared. Right? Okay. Now, if we change our variable, we can just write it. Also write x, y, z, w, such that x, y equals z w. So just move one of terms to the other side and just do this. Okay? And then what do we do? Okay. This is a threefold. Okay? Because you have four variables with one function. And it turns out 0 is the singularity of this threefold, but you can take a resolution. So the resolution we want is x tilde. X tilde is x, y, z, w, lambda mu inside C4 plus CP1 such that let me make sure there's a web page writing this formula. Never remember it, so I need to copy the formula here. Yes. Lambda, yes. Mu x equals lambda y, and mu z equals lambda w. Okay. So this is a resolution of this x, because you can project the first four components. The pre-image of any regular point it will be a 1-1 correspondence between the regular point and its resolution of singularity. Okay, good. So this is x tilde. This is the resolution of singularity. Okay, good. So we can also do this. Just do this. This is just the composition of this. And now we realize something. Okay, so something interesting happens. If we consider this morphism, okay, it covers this w to w square map. Okay, so it's a morphism between two families. And on the regular fiber of this family, it's just an isomorphism. On a singular fiber, it becomes a smooth resolution on the track. Okay. In other words, it resolves this singular family. After base change, the singular family can be resolved into a smooth family. Okay. And when we have a smooth family, of course, the monodromy is trivial, because it's a vibration of a disk. The monodromy has to be trivial. Okay. So this procedure is called simultaneous resolution, and it's some very special phenomenon that only happens for ADE singularities. Simultaneous. Okay, how to spell that? Simultaneous. Meaning that if you do a base change, you can resolve the whole family. Meaning that after doing you can find a smooth vibration which covers a branch cover in the base, and it maps smooth fiber isomorphically to the smooth fibers, and it is the resolution of a singular fiber. Okay. So it turns out that any ADE singularity has such simultaneous resolution, and whenever such simultaneous resolution exists, phi will be of finite order. So ADE singularity means you quotient C2 by a finite subgroup of F. For example, when gamma is just like C2, then this is exactly the singularity. Okay. Now, now what do I want to? So these are some backgrounds, and how I want to state a result proof using Seiberg-Witten theory.
Is there a more hands-on description of the diffeomorphism of X?
The which one?
The dentist.
The dentist. Does that depends on?
Is there a more hands-on description?
Oh yes, there is a more hands-on description. You can find that inside those notes. You basically, it's a geometric, okay, you consider the geometric flow on, geometric flow on this tangent disk bundle. You truncate that a little bit so that it is, when you restrict to the zero section, it's the antipodal map. And you multiply by some bump function and get the hands-on description of that. It's just you can really actually construct some Hamiltonian isotope on this cotangent bundle of S2. Okay. Yes, and now to state the result, I need to make another definition. We say f, a polynomial f is weighted homogeneous if there exist integers, positive integers called weights, w1, w2, w3 integers such that f p w1, z1, p w2, z2, p w3, z3 equals p to the power of p f z1, z2, z3 for any p. In other words, after putting a suitable weight on each variable, it becomes a homogeneous polynomial. One example is that this one. For example, that polynomial is weighted homogeneous because you can put weight QR on the first variable, PR on the second variable, and PQ on the third variable. Let the Milnor exotic sphere, that example is also weighted homogeneous. All right, now the theorem that can be proved using family Seiberg-Witten theory is assume 0 is an isolated singularity of weighted homogeneous polynomial. F from C3 to C. Okay. Suppose we have a weighted homogeneous polynomial with 0 being an isolated singularity. Then the monodromy is of a finite order. If and only if this singularity is ADE. Well, I would say, well, what we prove? We proved one direction. But the other direction is true because due to this problem. You can. The other direction is also true because you have we have that simultaneous resolution by Briscoe, Mattia, and many others. So we prove that any ADE singularity admits a similar resolution like this. So you can, after a base change, you can resolve the whole family and get a smooth fibration. So, for one example, is that suppose f is xp z1 plus z2 q plus z3r, then ADE, if and only if 1 over p plus 1 over q plus 1 over r is greater than 1. So the monodromy is a finite order if this quantity is greater than 1, and it's infinite order if this quantity is less equal than 1. For example, 2, 3, 5 is finite order, 2, 3, 6, 2, 3, 7 are infinite order. Okay? Any questions about the statement of this? So actually we have a conjecture. It's known that this kind of simultaneous resolution only exists for ADE singularity. For non-ADE singularity, you can never do this resolution of, you can never resolve the singular family into a smooth family even after base change. So this can be proved by, for example, by observing that the minimal resolution, if you have such a resolution, you will have a consequence that the minimal resolution of this singular fiber is the same, is diffeomorphic to the Milnor fiber. Milnor fiber. But associated to a singularity, you can consider about the minimal resolution, you can think about the Milnor fiber. If simultaneous resolution exists, then they must be diffeomorphic because one of them is a fiber over 0 and the other one is a fiber over some other term. They must be diffeomorphic. On the other hand, this is not true for, this is only true for ADE singularity, not true for other singularity. Okay? So this is the algebraic geometric proof. But it doesn't really, so motivated by this, so the question to this should be, for the conjecture, is yes, if and only if ADE. This monodromy have finite order if and only if it is of the singularity is an ADE singularity. We can prove this under the additional assumption that F is weighted homogeneous, but the conjecture is that this condition should really be unnecessary. Okay. All right. When did I stop?
45.
45. Okay, I have 2 minutes. Good. So then I can sketch the proof. I mean, I prefer to spend more time talking about backgrounds. Yeah, okay, so maybe let me talk about it. So, the proof goes like, okay, maybe let me just say a more general version of the theorem. Then the proof, then I think, yeah, then I think I will finish it. Okay, a more general version. So with that M, with that Y, you are cipher C manifold. We assume E1Y equals 0. For example, Y can be the Briscoe sphere I mentioned just now, and it can also be a singularity of the link there. Then with that M, be a symplectic fitting of this Y plus B C. So such cipher C manifold has a canonical context structure. And we consider a symplectic fitting of this context structure. So M is a symplectic manifold is bounded by Y. Now, one thing we can do is the following. So let me just draw a picture. M. This is a trivial neighborhood of Y. Okay. So now we can do a boundary then twist on this full manifold with boundary. So how to do that? How boundary? So it says 0, 1, Y cross Y by theta little y goes to theta at tau theta at y. So I need to explain this terminology a little bit. Tau is a cutoff function from 0, 1 to 0, 2 pi, which equals 0 near 0 and equals 2 pi near 1. This. And this is the, Y is a cipher 3 manifold, so it admits a circle action. Cipher 3 manifold is really just a circle bundle over a 2-dimensional orbifold. So it has a circle, canonical circle action. So this is just using the circle action. Okay. So intuitively, it's just a dead twist. Or you can imagine Y as a family of circles characterized by a 2-dimensional orbifold. So you can do a dead twist on all of these circles. So it's a generalization of the 2-dimensional dead twist. Okay. So let me just go to tau. Then the theorem proof using family Seiberg-Witten theory is this is infinite order in pi 0 of if M and E plus of M is greater than 0. Okay. As long as this symplectic manifold is not negative definite, this boundary then twist will be of infinite order. Okay. So this corresponds, when M is the Milnor fiber, this corresponds to a condition that geometric genus is greater than 0, and that's exactly when the singularity is not AE. And so this is proved by studying family Seiberg-Witten equations over the classified space of BG, where G is some C. Okay. And so this theorem implies this theorem because if you have a weighted homogeneous polynomial, then this boundary then twist is actually a power of the monodromy there. So if you can show this boundary then twist is infinite order, then that monodromy is also infinite order. So this is how we prove that theorem. We prove that theorem by reducing it to this theorem, and we prove this theorem by studying family Seiberg-Witten equations over these classified spaces. Okay, yeah, I think that concludes my lecture.